Sir, good morning.
Sir, okay, ma'am?
Sir,
Good morning,
after a
sir.
small prayer, we can start the session, sir.
Yes, okay, sir. PPT visible?
Okay.
PPT okay, sir?
Yes, sir, visible. Visible, sir,
Okay,
visible.
okay. Okay, sure.
Gerlin, you can do the prayer.
Okay, sir. Prayer. Almighty God, we thank you for this wonderful day. Be with us throughout this day. We thank you, Lord, for the gift of education that you have given us. Help us to study well and get good marks. Grant us the strength to overcome temptations. Help us to be pure in thought, word, and deed. Bless all our faculty members and our parents. We ask all these in the name of our Lord Jesus Christ. Amen.
Sir, start பண்ணலாமா? Shall we start, sir?
Yes, sir, we can start the session, sir. We can start.
Oh, thank you. Okay, sure. Good morning, students. So today we talk about transmission lines. So here we may expect 2 marks on the data. So I told for electromagnetic involves electromagnetic sphere view and antenna. So it is a combination of 3 different. Each time minimum 5 marks. Totally you can expect 15 marks. Score 10 marks in this, your gate score will go in a very good way. So we have to bother about these subjects. Right, the subjects is very simple. The problem with these subjects is mathematics and concept. Understand the concept. This subject is the simplest subject in the GATE examination, right, compared to other subjects. So we can score very good marks in this area. Today we will start with transmission lines, and I will solve a lot of problems, previous year GATE problems. Hope you understand everything. I want people to be interactive, right? Please ask some questions or a doubt, right? Then only it will be nice. No, for 3 hours I am only talking, just you are listening. That will not be fruitful for you. So, right? So please ask me some doubts if you are having any doubt in mathematics or wave propagation or lines. I want the session to be interactive, right? At least at the end of the class, ask some doubt, I will be happy. So I expect some doubt from you people in this class. Okay, let us start. So we will start with the transmission line. So what is transmission line? Transmission line is a guiding conducting structure, guided, can I call that is a guided conducting structures, right? Which is used to transfer power. Fine. So transfer power, or it is used to distribute power, right? At low frequency. At low frequency and in communication system and in communication system and at high frequency in computer networks, right? So at high frequency in computer networks. So just it is used to transmission lines are used to transfer or distribute the power at low frequency, right? Whenever you want to distribute power at a high frequency, what we have to do? We have to go for waveguides. Please remember, right? For high frequency, we have to go for waveguides. At low frequency, we can use transmission line. We know waveguide is used to transfer the power at high frequency. Which device will allow only high frequency? High pass filter, which blocks low frequency, and high pass filter allows high frequency to pass. So waveguide acts as a high pass filter, right? Whereas transmission line acts as a low pass filter. So this question they have asked many times in TRB exam. They asked, right? Because waveguide we can use it for only high frequency. Transmission line can be used at low frequency. So that's why waveguide acts as a high pass filter and a transmission line acts as a low pass filter. So this is a very important point we must know. Then we go and learn some other thing, right? So what is the general diagram of transmission line? So it will be like this, right? So this is fine. This is the transmission line equivalent circuit. It will go like this. So it is R, it is L, it is R, it is C. Sorry, it is not R. It is G, conductance. Okay. Fine. This is G. Right. This is G. So where R is resistance per unit length. That is very important, right? L is inductance per unit length. C is capacitance per unit length. And G is conductance per unit length. So this is the equivalent circuit of the transmission line. This also they have asked one time. So this we must remember, right? All these parameters are distributed all through the line. So all these parameters are distributed throughout the line. Please remember this point also. So they are all called the distributive parameters, right? Okay. Now from this we can find the two important parameter. What is that is impedance of the line, Z. That is equal to R plus J omega L. That is called the impedance of the line. Right? So another parameter is Y, admittance. That is equal to G plus J omega C. Right? So this is the equivalent circuit of the transmission line. Equivalent circuit of transmission line. Here the impedance is given by R plus J omega L. Admittance is given by G plus J omega C. Right? And these RLGC are called primary constant. So these are all the questions we expect regularly in TRB exam, not in GATE exam, right? So RLGC. These are all called primary constants. Whereas we have secondary constants. The secondary constants are Z0 and gamma, where Z0 is characteristic impedance, of a line, of transmission line, and I can call gamma as propagation constant. Right? So these constants we must remember. What are the primary constants of the line? What are the secondary constants of the line? Okay. Next. So the another thing is gamma is equal to root of z into pi. We know z is equal to r plus j omega l, and y is g plus j omega c. This is what how we are relating secondary constant. We know gamma is a secondary constant, R, L, G, C are primary constant. So this equation relates secondary and primary constant. Z naught is equal to Z by Y. That is R plus J omega L divided by G plus J omega C. These two equation relates primary and secondary constants. Fine. So this we must know. Right. Similarly, if you multiply these two equations, what will happen? Z naught into gamma. If you multiply these two equations, it will be R plus J omega L. This is what my gamma, G plus J omega C multiplied by R plus J omega L divided by G plus J omega C. This G will be cancelled. So it will be root of R plus J omega L into root of R plus J omega L. That is equal to R plus J omega L. So Z naught into gamma is equal to R plus J omega L. This is another equation. Fine. So next we divide gamma by Z naught. When you divide gamma by Z naught, what will happen? Gamma is R plus J omega L. This is G plus J omega C. When you divide, G plus J omega C will come to numerator and R plus J omega L go to denominator. So what happens? So these two fellows will cancel each other. So gamma by Z naught becomes, this is root G plus J omega C, root G plus J omega C, that is equal to G plus J omega C. Right? So this relation we must know. If they give one of the parameter, we must find the other parameters. So this is very, very important relations. Right? So in transmission line, we have so many equations. If you remember only equation, we can derive other equations. So first remember these two equations. So then we can understand other equations. Z naught into gamma is equal to R plus J omega L. Gamma by Z naught is equal to G plus J omega C. Right? So this is the first thing we must remember whenever you start studying transmission line. So whatever I teach today is the thing required for GATE examination. Right? So unwanted things I neglect. So what are all the basics we must know whenever you want to study transmission line? I bother about that only. Okay, fine. So next we will talk about lossless and distortionless line. These are all some types of transition lines. Okay, let us see what is lossless line and a distortion line. From here, the important things are starting. So this is the fundamental things we must know. So hereafter, the real thing come. Okay, first one is what is lossless line. A line with the following characteristics are known as lossless line. Right? So before that, I want to emphasize one thing here. I forgot to mention. Right here, I write with different color. So gamma is propagation constant. So I can write gamma is equal to alpha plus j beta. This is very important equation. Alpha is attenuation constant. Beta is phase constant. We have explained beta in a wave propagation itself in detail. Attenuation you know already. Attenuation is nothing but how much your wave gets attenuated. That is, the power is reduced or amplitude of the wave gets reduced. Attenuation is nothing but opposite to amplification. In amplification, you increase the amplitude of the signal, whereas in attenuation, the power or amplitude of the wave gets reduced. So how much your wave power of the signal or wave gets reduced when it is propagating from transmitter to receiver. That is given by attenuation constant. Shift per unit length. That's what we have studied. Lambda. So it is phase shift per unit length. I explained everything in detail in the last class itself, so we can just to understand the meaning, gamma is equal to alpha plus j beta. Okay, now we come to the lossless and distortionless line. What is lossless line? A line with the following characteristics are known as lossless line. For this lossless line, R is equal to G is equal to 0. That is the first thing, right? So resistance and conductance are 0 for lossless line. How it has come, the derivation is there, you refer the book. But for exam, you must remember these things only. For lossless line, R is equal to 0 and G is also 0. And conductivity is infinity. That's we must know. And third one is gamma is equal to J beta. Right? Why gamma is equal to J beta? Why alpha is equal to 0? Since it is lossless. Lossless means the power get not reduced. Right? So the power is not reduced or the amplitude is not reduced. Since amplitude is not reduced, there is no attenuation, right? Attenuation means reduction in amplitude. Since attenuation is not there, so attenuation is 0. We know gamma is equal to alpha plus j beta. Since alpha 0, gamma is equal to j beta only. Fine. And we know what is beta. Beta is equal to omega into root LC. Fine. This we know already. So fifth property. So first, these are all the properties you must know. Then phase velocity, Vp is nothing but phase velocity. This we dealt in the wave propagation itself. Phase velocity is equal to 1 by root LC. Right? So that's what. Why? From this you can understand. We know V is equal to omega by beta. So from here, omega by beta will become equal to 1 by root LC. So that's what phase velocity. Fine. Sixth one, characteristics impedance. Z0 is equal to root of L by C. Why Z0 is equal to root of L by C for lossless line? Because we know in lossless line R0, G0. General characteristic equation formula is R plus J omega L divided by G plus J omega C. R0, G0 means what will happen? So here R0, G0. So J omega cancel. So root of L by C. A line with these characteristics are known as lossless line. Right? So this is a thing we must remember about lossless line. Next. Let us talk about distortionless line. For distortionless line, R by L is equal to G by C. This is very important point. Right? A line is called distortionless line if R by L is equal to G by C. Similarly, for lossless line, we must know this parameter very clearly. We must know this parameter very clearly because these are all primary constant. So sorry, it's secondary constant Z naught and gamma. So these value we must know. And for lossless line R0, G0. This is for distortion lines. R by L is equal to G by C. Right? And the second property is alpha is independent of frequency. That is, alpha is attenuation. Attenuation is independent of frequency. Fine. This is a very important parameter. And alpha, beta is a function of frequency. Already we know beta. Beta is always a function of frequency. So here in distortion line, this line, alpha is independent of frequency, beta is a function of frequency. This parameter we must know. Third one is alpha is equal to root RG. This is very important parameter. Right? Whereas here alpha 0. For lossless line, alpha 0. Whereas in what do you call distortionless line, alpha is equal to root LG. Fourth parameter, fourth thing is beta same. Beta is equal to omega. So we know that beta is a function of frequency. Alpha, you see, alpha is independent of frequency. Frequency independent, alpha is equal to root RG. Beta, function of F. So it is independent of F, it is depending on F. Okay, fifth one, phase velocity Vp, that is equal to 1 by root LC. Right? So, you know, another important parameter is Z naught. Z naught is equal to root of L by C. We know from here you see LC is equal to, you bring L here, C here. So what will happen? L by C is equal to R by G, cross multiply. L by C is equal to R by G. So I can write Z naught is equal to L, root of L by C, that is equal to R by G. Right? So these are all the characteristics of distortionless line. Right? So please understand all the parameters because we are going to deal with the lossless line only all through our line. We assume that our line is lossless line. So all these parameters must be known. Then only we can solve the problems. So R is equal to 0, G0, attenuation 0, gamma is equal to J beta, Z naught is equal to root of L by C. Similarly, a line is called distortionless line, R by L is equal to G by C. Right? So please remember this parameter. Okay. Next. So another important point we must remember is the conversion we use regularly in a transmission line, Nepper and decibel. So 1 Nepper is equal to 8.686 dB. Similarly, 1 dB is equal to 0.115 Nepper. Right? So this definition you must know because in the exam they may give Nepper and ask you to find the answer in dB conversion. So this conversion we must know. Right? So this is a very important point. Now we come to the important formula. This is the formula we are going to use to solve most of the problems, right? So what is that? Is input impedance of different load. Okay, so you take a type of a line. Here we take type of a line, type of transmission line, and we write input impedance. Right. So first we go for lossy line. If a line is lossy, there is some losses, power loss, right? So for that, input impedance is equal to Z naught plus, sorry, ZL. It is this is a very, very important equation. We use mostly this equation, right? Z naught into ZL plus Z naught tan H gamma L divided by ZL, sorry, right, this is Z naught plus ZL tan H gamma L, right? So this is what input impedance of a lossy transmission line. So Zin is equal to, this is a table, right? So Zin is equal to Z naught into ZL plus Z naught tan H gamma L divided by Z naught plus ZL tan H gamma L, right? For lossless transmission line, lossless. What is lossless line? Where attenuation is 0. Just now only we have studied. For that, Zin is equal to Z naught into ZL plus JZ naught tan beta L divided by Z naught plus JZL tan beta L. Fine. So you see the difference. What is gamma here? If you substitute gamma is equal to alpha plus j beta, for lossless line, alpha 0. So gamma is equal to j beta. So tan H j beta L, tan H j beta L is equal to j tan beta L. That's what I have done here, right? So only this equation is enough to remember. From that, if you substitute, instead of gamma is equal to alpha j beta, tan H j beta L becomes j tan beta L. So that's what it is, lossless, right? So these two equations are very, very important. Fine. So this is Zin formula. Input impedance equal to this one. Fine. Next, so input impedance of a different load. Next thing we have to remember is, if a line is lossy, right? Here the load, I don't talk about load, right? Simply consider the line is lossy. Here the line is lossless. That's what I have done, right? Now we consider if a line is lossy line, but load is short circuit. Load is short circuit means what? Impedance is 0. So that is load impedance is 0. Under that condition, what is Zin value? Zin is equal to, you see ZL 0. So again use the same formula. If ZL 0 means what will happen? You substitute here. So this one gone, this one gone. Fine. So these two will be 0. So Z naught square divided by Z naught. So it is Z naught tan H gamma L. So my Zn is equal to Z naught tan H gamma L. Right? How? Let us do here. Zn is equal to, for general, Z naught ZL plus Z naught tan H gamma L divided by Z naught plus ZL tan H gamma L. If ZL 0, this will be 0, this will be 0. So Z naught into Z naught tan H gamma L divided by Z naught. These two will be cancelled. So what I get is Zn is equal to Z naught tan H gamma L. So this is for a lossy line with short circuit load. Right, I write here Z not tan H gamma. Right. Similarly, I can write Zn is equal to ZSC, short circuited impedance. Similarly, for open circuit load, if load is open circuit, ZL is equal to infinity. Right. So substitute ZL is equal to infinity here. What we get is ZOC is equal to Z naught cot H gamma. That is what our input impedance. Right, let me do that. So what is Z in? Z in you see here tan H gamma L. Tan H here ZL I substitute infinity, so it will become infinity. If I substitute here also infinity, it is infinity by infinity. So it is very difficult to do that. So I take tan H gamma L outside. Z naught is there already. Z naught tan H gamma L outside from the numerator. So it will become ZL by tan H gamma L plus Z naught. Similarly, in denominator, I take tan H gamma L outside. Tan H gamma L. Fine. So, what will happen? Z naught and plus, it is Z naught plus Z. Z naught by tan H gamma L. Right. So, if you simple like that, if you solve, what you get is ZOC is equal to cot H gamma. Fine. So, this is the way we have to solve this problem. Fine. And last one is, let me do that. Yeah. What happens when the condition is matched? Right. So, when the load is matched condition, that is lossy matching means load impedance must be equal to characteristics impedance. Sorry. When load impedance matches with the characteristics impedance, then that condition is called matched condition. Right? This is a very, very important point. Load impedance must be equal to characteristics. When ZL is equal to Z naught, what becomes is Zin is equal to Z. Right? Here you see, when you substitute ZL is equal to Z naught, what will happen? So from this formula, ZL is equal to Z naught, if you substitute Z naught, for this ZL you substitute Z naught plus Z naught tan H gamma L divided by, similarly, Z naught plus, instead of ZL you substitute Z naught tan H gamma L. These two will be cancelling, so Zin is equal to Z naught. So these are all the 3 points we must remember in lossy transmission line. So what will happen to the input impedance for a transmission line, lossy transmission line with the short circuit load? It will be Z naught tan H gamma L. For open circuit load, input impedance is equal to Z naught cot H gamma L. Matching condition, Zin is equal to ZO. You see how to remember whether it is tan H cot H. Simple logic is for O, there will be O. Open circuit to open. So for open circuit, it is cot H. For short circuit, it is tan H. Just a shortcut method, right? Okay. This is for lossy. Now we come for lossless transmission line. Input impedance of lossless line. Shall I drink some water? Okay, for lossless transmission line, what is it? So first you find short circuit load. Short circuit load means ZL is equal to 0, right? So for lossless transmission line, what is the general? This is the general input impedance. This is general impedance of transmission line. First I write Z is equal to Z naught ZL plus J tan theta L divided by J Z naught. Z naught plus J ZL tan theta L. Here ZL is equal to ZL 0, this will be 0, this will become 0, Z naught will be cancelled. So what I get is Zn is equal to J naught tan L. Similarly, for open circuit load, ZL is equal to infinity, where Zn is equal to minus Jz naught cot beta L. Fine. And the match condition, that is when ZL is equal to characteristics impedance. This is called the match condition. When load impedance, ZL is load impedance, Z naught is matches characteristics impedance. That condition is known as matched line. Line is known as matched condition. That is known as condition. So this will be a very, very important point. This is equivalent to parallel resonance, right? And this is equal to series resonance. Let us see all the things. So this is equal to short circuit impedance. Zn is nothing but short circuit impedance. This is ZOC, open circuit impedance. So many parts. Okay. So this is 3, 4, this is always same. So just don't that will come from the same. But what is the characteristic impedance of a there's no lossless time. Z is equal to root of L by C, right? So this is what the lossless transmission. This question they have asked in exam. Yeah. Lossless transmission of 50 centimeter and is equal to this one, C is equal to this one, is operated at 25 megahertz. What is the error path? So C, what is the thing that 50 centimeter. So L is equal to 50 this 50 10 power minus 2 meter. L is equal to 10 microhenry, C is equal to 40 picofarad. L is equal to 10 microhenry, 10 into 10 power minus 3 henry. C is 40 picofarad, right? 40 picofarad per meter. You see, everything is given in the per unit length meter. Per unit meter, right? So, primary car. L is 55 megahertz. So it's a lossless with this. What is the electrical length? So earth length is nothing but beta into L, which is. Am I audible now? Can I start? Okay, thanks for the response. Uh, Let us see this question. This is a very, very important and beautiful question. This type of question only you can expect in GATE exam. Here you see all transmission line section in figure have a characteristics impedance of R naught plus J naught. Right? This is given. So all the lines are having Z naught characteristics impedance equal to R naught. And here also Z naught is equal to R naught. Here also Z naught is equal to R naught. Right? What is the input impedance they are asking us, right? So let us see, whenever they ask problem like this, you have to start from load end, right? So from right hand side, you have to start here. Don't start from source end, right? Okay, we start from a load end. Here you see what is, let us start from here. This is a lambda by 4 line, right? Okay. So case 1, let us start case 1. What is the length? Length is equal to lambda by 4. Z naught is equal to R naught for all the lines, right? What about load impedance here? Load impedance is R naught by 2. So ZL is equal to R naught by 2, right? For that, I find the input impedance. They are asking overall input impedance here. Here, what is the input impedance that they are asking? So first, I have to find what is the input impedance here. Let us assume this is Z1, Z in 1. This is input impedance Z in 2. Right? From only this is a load impedance. This ZN1 and ZN2 are parallelly connected here. So this is acting as a load impedance for lambda by 8 line. From that only I can find Zn. That's why we are starting from here, right? So what is the formula for Zn? We know Zn is equal to Z0 ZL plus J Z0 tan beta L divided by Z0 plus JZL tan beta L. So your Zn depends on ZL. Input impedance depends on load impedance. So when you want to find Zn, I want what is the impedance at this point. That is, this load impedance is the input impedance for this line and this line. So first I have to find the input impedance for this line and this line. That is a load impedance for this line. So then only I can find what is Zn. So first I find Zn1. So this is what Zn1, input impedance of this segment. Zn2 is the input impedance of this segment. These two input impedance are acting as a load impedance for segment 3. Right? From that only I can find Zn. Okay, first I find case 1. Here I have L is equal to lambda by 4. Z0 is equal to R naught. ZL is equal to R naught by 2. Right? Substitute. Z0 is equal to R naught ZL plus J R naught tan beta 2 pi by lambda. L is lambda by 4 divided by Z0 R naught plus J ZL tan 2 pi by lambda into lambda by 4. Right? So cancel lambda 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 lambda. Right? So tan pi by 2. Tan pi by 2 is infinity. Numerator is also infinity. Whenever you get the tricky situation like this, take that factor outside. So R naught, I take tan pi by 2 outside. So it will become J R naught plus ZL by tan pi by 2. Similarly for denominator, I take tan pi by 2. J ZL plus R naught divided by tan pi by 2. Right? So this tan pi by 2, tan by 2 cancelled. Tan pi by 2 infinity, ZL by infinity 0. So this will be cancelled. R naught by infinity 0 cancel. So this indicates JJ cancel. R naught square. R naught into R naught square, ZL. ZL is nothing but R naught. Right? So what I get is R naught. Fine. So this is the first thing we have to remember. Right? So what is the ZL? R naught by 2. So R naught by 2 because ZL is R naught by 2. So these two are cancelled. So it will be 2 R naught. So what is the impedance I am getting? Impedance I am getting is 2 R naught. Right? Similarly, I have to find Z in 2. So Okay. So I consider this 2 R naught is Z in 1. So Z in 1 is equal to 2 R naught. Similarly, we find for case 2, what is the thing happening? Z naught is R naught for all the condition. L is equal to lambda by 2. ZL value we will see. Here ZL is 2 R naught. This is load impedance. L is equal to lambda by 2. Z naught is R naught. ZL is 2 R naught. 2 R naught. So what is input impedance? Z in ZL. ZL is nothing. Z naught. Z naught is R naught. ZL 2 R naught plus J Z naught. Z naught is R naught tan beta L. Beta is 2 pi by lambda into lambda by 2 divided by this is Z naught. Z naught is R naught plus J ZL. ZL is 2 R naught tan 2 pi by lambda into lambda by 2. I substitute in the same equation. So pi cancel. This is lambda cancel. 2 cancel. This is tan pi. Tan pi is 0. So totally this parameter will be out. This parameter will be out. So that is equal to 2 R naught square divided by R naught. So it is 2 R naught. So in this case 2. So I write as Z in 2 is equal to 2 R naught. Fine. So now what is the impedance here? 2 R naught. So 2 R naught is the input impedance of section 2. 2 R naught is the input impedance of section 1. You see this is connected to here and here, right? So this is a input impedance, this is a load impedance. So you see section 1 is connected in parallel with the section 2, right? 1 and 2 are in parallel, right? This area is a load impedance for section 3. So here what are the two impedance? One impedance is 2 R naught, another impedance is also 2 R naught. These two are parallel. So what is ZL? ZL is 2 R naught parallel to R naught. This impedance is 2 R naught, this impedance is also 2 R naught. These are connected in parallel. So 2 R naught parallel to R naught is R naught. So for third condition, ZL is equal to R naught. Okay. So let us go to case 3. Case 3 is Z naught is equal to R naught, L is equal to lambda by 8, ZL is equal to R naught. Just now only we found, right? So follow the same procedure and substitute here, and what you will get is Z in ultimately you will get 2R naught. That is the final answer, right? You substitute all the parameters in the equation, what you get is 2R naught. So the answer is option D. In this way only you have to solve. In the exam they ask this type of questions only, so please understand the logic. Okay. Sixth one, a transmission line has a characteristic impedance of 50 ohm. So Z naught is equal to 50 ohm. And resistance R is equal to 0.1 mho per meter. You see everything with respect to length. If a line is distortionless, what is the attenuation constant? We know for distortionless line, alpha is equal to R into G. Fine. So R into G. What is, they have given only R. G we don't know. From Z naught we have to find. How can we find Z naught is equal to, we know, L by C, that is equal to R by G. R by G is equal to Z naught. This implies, right? So what is G? G root G. Root G. This root G I bring this side. Root G is equal to what you call root R by Z naught. You relate these two equations. Root G I bring this side. Root R by Z naught. Okay. So what will happen? Therefore, alpha is equal to root RG. Root R I write as root R. Root G is nothing but root R by Z naught. Root R by Z naught. This is R by Z naught. What is R? R is equal to 0.1, Z naught is 50. R is equal to 0.1, Z naught is equal to 50. So attenuation is 0.002 Nepar per meter. So the answer is option B. Attenuation unit is Nepar per meter. Right? So the attenuation constant is Nepar per meter. Please remember. Okay. Next one, you see a characteristic impedance of a transmission line is 50 ohm. So Z naught is 50 ohm. Input impedance of a open circuit line. So ZOC they have given. ZOC is equal to 100 plus J 150 ohm. When the transmission line is short circuited, what is the value of the input impedance? So they ask what is short circuit impedance. So when line is short circuited, what is the this one? So we must remember one important relation that is given by Z is equal to ZO is equal to ZOC root of ZSC. Right? We have already found ZSC and ZOC. If you multiply and take the square root, what you get is Z naught. Right? So this is very, very important. Please remember. Right? I didn't derive, but this is the equation. Hope you should have remembered. As a final year student, you must have come across this equation. So what they are given in the equation, they are given Z naught they are given, ZOC they are given, ZSC we have to find. So from this, ZSC is equal to ZO square divided by ZOC. ZO they are given 50 square divided by ZOC is 100 plus J 150. So what you get is 50 by 2 plus J3, right? So I it is 50 into 50 divided by 50 I take outside 2 plus J3. So that if you simplify, what you get is 7.69 minus J 11.54. So 7.69 minus J 11.54. Next question is another important question. You see one end of the lossless transmission line. So the line is lossless, having the characteristics impedance of Z naught. Z naught is equal to 75 ohm. L length is 1 centimeter short circuit. L is 1 into 10 power minus 2. Right? Frequency they have given 3 gigahertz. Right? So they have given Z naught, L, you see, and it is short circuit. Right? Lossless short circuit line. What is the input impedance at the other end of the line? So what is the nature of input impedance? That's what they are asking. We know for short circuit line ZSZ, what is for lossless line, what is input impedance? ZSZ is equal to J into Z naught tan beta N. Right? This is what short circuit. For open circuit, for lossless line minus J Z naught cot beta N. Hope you remember. I told open means cot. So here they have shorted the input impedance. So shorted the load. So Zn is equal to ZSC, J Z naught tan beta N. Z naught we know, L we know, beta we have to find and substitute. So I have to find ZSC is equal to J Z naught tan beta L. Beta is equal to 2 pi by lambda. Beta L. Let us directly find beta L. 2 pi by lambda L. 2 pi by lambda. Lambda is C by F. C is 3 into 10 power 8. F is 3 gigahertz. 3 into 10 power 9. This is what lambda. L is, what is the L? 1 centimeter. So 1 centimeter is 10 power minus 2. What you get is, if you simplify, it is 0.1 beta L. Fine. So beta L is equal to 0.1. Now you substitute Z naught J 50, right? And what do you call? So sorry, this lambda is 0.1, please now, right? This is 0.1. So 2 pi by 0.1 into 10 power minus 2. 10 power minus 2 I write as 1 by 100. So that will be equal to, that is 6 degree or pi by 5. Pi by 5. Okay. So now beta L is equal to 36 degree. So tan 36 degree or pi by 5. Now you see ZSC is equal to JZ50 tan pi by 5. Right? So the impedance is positive in nature. If impedance is positive, then that is known as inductive. If the answer is in minus J tan, some answer means it is capacitive. So it is plus J tan pi by 5. So impedance is positive. We know the reactance for inductance is positive. So it is inductive in nature. If the answer, if we got it in the minus, it will be capacitive in nature. So option D is the right answer, right? So in that way we can, so they may give lossless, short circuit line or open circuit line, anything they give and ask you to find the answer. Okay, now we come to the second point. Fine. What is return loss, reflection loss, and reflection factor? Okay. So, what is return loss? These are all the things we must know. Return loss is nothing but the difference between forward power minus reflected power. Right? So we have a transmitter, here we have a receiver, right? So when the power, it is forward, right? When the line is not matched, what will happen? We studied in impedance matching. When line is not matched, what will happen? The power will get reflected, right? So this is forward power, this is reflected power. The difference between forward power and reflected power is return loss. Suppose in the forward direction you are sending 30 dBm and 10 dBm is reflected. So what is return loss? Return loss is equal to 20 dBm. Forward power is 30, 10 dB is reflected. Suppose 5 dBm is reflected, what will happen? Return loss is equal to 25 dBm. From this, what we understand, when reflection is very less, the return loss is more. So return loss, high return loss indicates very good line, because the power is not reflected, right? Reflection is very less means the return loss is more. So reflection very less means all the power is delivered to the load. So the line is, I think, very good line, matching line. So for a good line, the return loss must be very, very high. This is the first thing you must know. High return loss means very good line. Suppose 20 dBm reflector means what will happen? Return loss is 10 dBm, right? For 20 dBm reflection. So what is the meaning? Out of 30, 20 is reflected. So only 10 dBm is delivered. It is very poor line. So return loss is less. So return loss means it should be having very high value. Okay, that is the first thing. The formula for return loss is very, very important. Based on this, they are asking some question. 20 log minus 20 log of gamma. Gamma is reflection coefficient. I will deal about gamma later, right? So minus 20 log of gamma. Okay, next one is return loss. This is the thing you must know. This formula is very, very important. Note down. Minus 20 log of gamma. Next, reflection factor and reflection loss. Right? Reflection factor is given by K, that is equal to Z1 root of Z1 into Z2 divided by Z1 plus Z2. Right? So it indicates change in the load current. So change in the current at the load or load current due to reflection. Due to reflection because of the mismatching at the mismatched junction. Right? So it is nothing but reflection factor is nothing but change in the current. right? So change in the current at the load due to the reflection at the mismatched junction. This is what reflection factor. There is another one parameter we must know, reflection loss. This is impedance, source impedance and load impedance. Z1 is source, Z2 is load. So reflection loss, that is given by, simply it is nothing but a dB value. 20 log of modulus Z1 into root of Z1 into Z2 divided by Z1 plus Z2. Right? Take the 20 log, you get reflection loss. So these are all the parameters you just remember. But return loss is very, very important. Reflection factor, just you know. Okay. Next, VSWR. This is very, very important. Before understanding VSWR, we must know reflection coefficient. Gamma. Right? So reflection coefficient is out of power incident, it is a ratio of power incident, sorry, power reflected to the power incident. So it is reflected power divided by incident power. Right? Suppose you are transmitting 20 dB of power, and out of that 10 dB is reflected. So that means what is the reflection coefficient? 1 by 2. Clear? Suppose if you are transmitting 20 dB, out of that only 5 dB is reflected. What is the reflection coefficient? 1 by 4. That is 0.5. This is 0.25. So what is the thing? Reflection. What is the maximum reflection can take place? 20 dB means maximum reflection is 1. Right? All the 20 dB is reflected. So it is maximum value. What is the minimum value? 20 dB. Nothing is reflected. 0. So 0. Reflected is 0. Incident is 20. So reflection coefficient range from -1 to +1. Right? Same reflection in opposite direction. So -1 to +1. This implies magnitude of reflection coefficient is always less than 1. Fine. So it is in minus means opposite direction. So gamma varies from -1 to +1. So mod gamma will be always less than 1. It's very, very important point. Reflection coefficient will not be greater than 1, both in positive direction and in negative direction. So this is the thing first we must know. Right? So it is the ratio of reflected power to the incident power. Out of this much incident power, how much power is reflected? That is given by reflection coefficient. Next one is voltage standing wave ratio. VSWR. VSWR. So before that we must know gamma is given by ZL minus Z0 divided by ZL plus Z0. This is the formula. This formula we use widely. Fine. What's the time? Okay. So ZL minus Z0 divided by ZL plus Z0. Okay. Now voltage standing wave ratio. It is a symbol is S. S is nothing but voltage standing wave ratio. That is given by ratio of maximum voltage to the minimum voltage. Right? Or it is a ratio of maximum current to the minimum current. Fine. So S is given by, in terms of reflection coefficient, 1 plus mod gamma divided by 1 minus mod gamma. These are all the relation which is widely used in the exam. Gamma is equal to S minus 1 divided by S plus 1. Right? You see, reflection VSWR is always greater than 1. You see, 1 plus something, 1 minus. So it is greater than 1. Numerator is greater than 1. Denominator is less than 1. So denominator is very small, numerator is very large. So S is always greater than 1. So S varies from 1 to infinity. Why? What is the minimum value of gamma? Gamma will be having a minimum value of 0. So 1 plus 0 divided by 1 minus 0, 1. So minimum reflection coefficient is 1. Right? Maximum, when gamma is equal to maximum, what will happen? Maximum is 1. So 1 plus 1 divided by 1 minus 1. So infinity. Right? So you see, S is equal to 1 plus gamma divided by 1 minus gamma. Gamma 1 implies complete reflection. All the power is reflected. Because gamma is equal to PR by PI. When all incident power is reflected, PR is equal to PI. PI is a PI gamma 1. So gamma 1 is equal to 1 means all the power reflected. So 1 plus 1 divided by 1 minus 1, infinity. So S tends to infinity means total reflection. So this means very poor line. The line is absolutely poor. S is equal to 0 means what? When we will get S is 0, S is equal to, sorry, S is 0 will not be there, S is equal to 1. When gamma is 0, so 1 plus 0 divided by 1 minus 0 is 1. So gamma 0 indicates what? Gamma 0 means, what is the meaning? PR by PI. When PR is equal to 0, then only gamma will be 0. So incident power is, what is reflected? The reflection is 0. So reflection 0 means good line. So S is equal to 1 means no reflection, and it is a very good line. Fine. So you see, when gamma will be 0, we know gamma is equal to 0 is possible. Fine. Gamma is equal to ZL minus Z0 divided by ZL plus Z0. When gamma will be 0, ZL is equal to Z0. When ZL is equal to Z0, it will be 0 by this one, 0. So you see ZL is equal to Z0 means matching, matched condition. We know when the kind of load impedance and source impedance are matched, maximum power transfer takes place. That's what. So when gamma is equal to 0, maximum power transfer will take place. That means there is no reflection. That's why this condition. So this is very, very important. What is S is equal to infinity? S is equal to infinity means the transmission line is very, very poor. Standing wave ratio is infinity. It is very poor line. Standing wave ratio is 1. It is very good line. So S should be minimum for very good line. Right? So that is the thing we must know. Okay. So this is what we must remember. Okay. Next, we will solve some problems, right, in VSWR. So what is the first question? So it is very, very easy question. What they are telling? VSWR can have a value between, just now only we saw, it is varying from 1 to infinity, right? So simple. Second question, the return loss. The return loss of a device is found to be 20 dB. R is equal to 20 dB. The VSWR and magnitude of reflection coefficient. They ask what is S value, what is gamma value, right? Just now only I told what is return loss formula. Return loss is equal to 20 log gamma, right? So return loss is equal to 20. It is a loss, so you put minus. So 20 is equal to minus 20 log of gamma. This implies log gamma is equal to minus 1. This is gamma is equal to 0.1. So reflection coefficient is 0.1. So this is not the answer. Out of these three, one must be the answer. You see, S must be greater than 1 only we know. So greater than 1.22, so it is 0.1. So S cannot be less than 1. So this is also wrong answer. In that way, we have to neglect the answer. So it must be either plus 1.22 or minus 1.22. Let us see. So S is equal to 1 plus gamma, that is 1 plus 0.1 divided by 1 minus 0.1, that is equal to 1.22. So the answer is option A. So you must know how to neglect the wrong answer also, right? So by seeing the question itself, standing wave ratio cannot be this one because S is less than 1. So this is not an answer, right? So immediately you can neglect that answer. Third question, a transmission line of pure resistive, right? So, okay, this is very important only. Yeah, transmission line of pure resistive characteristic impedance, right, is terminated with the unknown load. So Z0 is purely resistive. The measured value of VSWR on the line is equal to 2. So VSWR is equal to 2. And voltage minimum point is found to be at the load. V minimum is at the load. What is the nature of the load impedance? Right? So you see, if it is, they have given the characteristic impedance is purely resistive. V minimum at the load. Let us deal about V minimum and also when voltage minimum or voltage maximum occurs at the load only when load is purely resistive. I will tell you why. So load is purely resistive. So the answer is option C. Please note down this question. I will explain the answer in the later part. Okay. Okay. Next. A transmission line of characteristics impedance 50 ohm. Fine. So this is some critical question, I think. Okay. Characteristic impedance 50 ohm is terminated in a load impedance Z0. VSWR is 5. And first of the load minimum is observed at a distance of lambda by 4. Okay, this question and all I will deal later, right? So some of the thing I have to explain, then only I can explain. Okay, this we will see. Yeah, the lossless line with 50 ohm. Okay. Line of 50 ohm means characteristic. It is talking about 50 ohm, Z0 50 ohm. Terminated with a load of 100 ohm. ZL is equal to 100 ohm. What is VSWR? Yes, they ask. We know S is equal to 1 plus gamma mod gamma divided by 1 minus mod gamma. So first we have to find gamma. Gamma is ZL minus Z0 divided by ZL plus Z0. ZL is 100, Z0 is 50, 100 plus 50. So 50 by 150, 1 by 3. So gamma is 1 by 3. You see, answer is less than 1. Gamma must be less than 1. Okay. S is equal to 1 plus gamma, 1 plus 1 by 3 divided by 1 minus 1 by 3. So it is 4 by 3. It is 2 by 3. 3 key cancel. 4 by 2 is equal to 2 by 1. So the answer is 2 is to 1. Right? The ratio is VSWR is 2 is to 1. Okay. Next question you see yeah, 50 ohm lossless line. So it is line impedance is nothing but characteristic. So Z0 is equal to 50 ohm. It has pure reactance at its load. So ZL is equal to J 100. What is VSWR? So Z0 JL they have given. So what is gamma? ZL minus Z0. So J 100 minus 50 J 100 plus 50. So take minus outside. So it will be J2 50 outside J2 minus 1. This is J2 plus 1. Right? See, this is very important problem. Hereafter don't do all the complex conjugate and all. Let me tell you why. Because S is equal to 1 plus mod gamma divided by 1 minus mod gamma, magnitude. So keep this as it is. What is mod gamma? It is square root of A square plus B square. 2 square plus 1 square. What is the magnitude of the denominator? 2 square plus 1 square. So that is 1 only. Here or not? So directly you can find. If you take conjugate and 10 you find mod gamma, no use. So don't waste your time. So here you note this point. When numerator and denominator have same number, 2, 1, even though it is 1, 2, the square root will be same only. So here 1 plus 1 divided by 1 minus 1 is infinity. Right? So the answer is infinity. Right? You note down problem number 6 and 7. I will come to the conclusion later. You see 7. Again, you see the characteristics impedance is 50 ohm. Z0, 50 ohm. Terminated by load. Load is J50. J50 ohm. What is VSWR? So if you want to find VSWR, first find gamma. ZL, J50 minus Z0, 50. J50 plus 50. Again, you see, don't simplify anything because both our numerator and denominator are having the same number. So this implies what is mod gamma? Mod gamma is real part square 50 square plus imaginary part square 50 square. real part minus 50. So minus 50 squared, imaginary part 50 squared. Similarly, real part square 50 squared plus imaginary part square 50 squared. So this will be giving mod gamma is equal to 1. So when mod gamma is equal to 1, what happens? S is equal to 1 plus gamma, 1 minus gamma infinity. So what is your understanding from problem number 6 and 7? You see, whenever you have a load is terminated by purely reactance, not resistance and impedance. Impedance means we will have resistance plus reactance. Here resistance is 0. You see, when the load is purely terminated by reactance J50, here you see it is terminated by J100. What is the S value we are getting? Infinity. So you don't need to solve this type of problems. Directly you can write. So in the exam, if they ask 2 times they asked this type of question, so don't solve this type of question. Directly you write VSWR will be infinity and S must be equal to 1. Okay. So gamma must be equal to 1. So gamma must be equal to 1. S must be infinity. Whenever your load is terminated by reactance. Fine. This is very, very important conclusion. Okay. So this question will be later if time permits. Time around 45. Okay. Hopefully time permits. Next you see a uniform plane electromagnetic wave is incident normally on a plane surface with the dielectric material is reflected with the VSWR of 3. Right? So you see a plane wave incident normally with S is equal to 3. What is the percentage of power reflected? How much it is reflected? That's what they are asking. This is a beautiful question, right? So S is equal to 3 they told. They ask reflected power. So from S we can find gamma. Why we are finding gamma? Let me tell you. Gamma is equal to S minus 1 divided by S plus 1. So what is that? So S is equal to 1 plus gamma divided by 1 minus gamma. So what they have given? VSWR. So VSWR is 3 minus 1 divided by 3 plus 1, 2 by 4. That is 1.5. Power reflected is by PR by PI is given by gamma square. We remember this equation. Right? So power reflected is equal to how much is reflected PI is incident. 0.5 is equal to 25%. So then see in the last class only we will see what is the incident. So if the condition is about 3, then only the power reflected. So that is option. Okay. This is having a characteristic of 50. And kilowatts of power equal to 10 kV, 10 into 10 power 3 watts. At 100, so S equal to 100 into 10 power 3 hertz. So maximum value of RMS current along the line is I. They have given I is equal to 20 ampere. What is the VSWR? We can tell. So we have transmission that is 51 and they have to deliver 10 power at a frequency of 100 kilohertz. We can take so what is the VSWR? So this is equal to 1 plus mod gamma divided by 1 plus mod gamma. I want to find S. If I want to find S, I need mod gamma. That is ZL. Here load distance ZL. Right? It is a line. With the load they didn't give, but they have given I and the power. Power is equal to 10 kilowatts, right? 10 kilowatts. So 10 so the I square will come down. I is nothing but sorry, I is nothing but what is the answer? I is 20 ampere. 20 into 20, 20 square, 400. Okay, so this indicates ZL is equal to 25. Now we got ZL. What is there one? So gamma is ZL minus Z0 divided by ZL plus Z0. So 50 minus 25, sorry, ZL 25, 25 minus 50 divided by 25 plus 50 minus 1 by 3. So S is equal to 1 plus mod. This is gamma. Mod gamma is 1 by 3. So 1 by 1, that is very important. Don't put minus 1 by 3, right? Mod gamma 1 by 3. So 1 minus 1 by 3. So 4 by 3 divided by 2 by 3. So S is equal to 2. So the answer is S is equal to 2. This cannot be answered because VSWR must be greater than 1, right? Okay. Next question, you see if the reflected wave at the load of a transmission line is 20 dB below the incident wave, right? So what is VSWR? Reflected wave is 20 dB below the incident wave. We know VSWR is Vmax by Vi or VR by Vi. So it is 20 dB below. 20 dB below means it is minus. This minus indicates minus below. Above means plus 20 dB. Please understand. Right? So this is what 20 log gamma. Why I put 20 log instead of gamma? PR by VA reflection coefficient. So what is the thing? Why I put that? Because it is a dB unit. Right? So I convert it to dB. So 20 is a 20 log of gamma, right? So reflected wave, reflection coefficient only they are 20 dB below. So please remember this is a reflected wave. So out of the transmitted wave, this much is reflected. That is 20 dB below the incident wave. So VR by VA is minus 20, which is nothing but our reflection coefficient, not S. Sorry. So this is 20 log VA gamma. Fine. Why I put 20 log? Because the unit is in scale, dB scale. So 20 log. So this implies gamma is equal to 20 minus 1 10 power minus 1. That is fine. I can do scale. So gamma is equal to 0.1. Why? Log gamma is minus 20 divided by 20 minus 1. So gamma is 10 power minus 1, that is 0.1. Gamma is equal to 0.1 means what is VSWR? Just now only we have studied in the previous problem. It is 1.22. Otherwise, you substitute S is equal to 1 plus gamma divided by 1 minus gamma. 1.2. Fine. This is it. So only thing we must remember is it is minus because it is below. If they give 20 dB above, put plus. Okay. Next question, if a transmission line terminated with a load equal to characteristic impedance, what is the reflection coefficient? Reflection coefficient is ZL minus Z0 divided by ZL plus Z0. What they are telling? Terminated with load is equal to characteristic impedance. That means ZL is equal to Z0. ZL is equal to Z0 means numerator 0. So the answer is 0. Fine. Okay. Next one, for a line characteristics impedance Z0 terminator with the load ZR such that ZR is greater than Z0. What is the standing wave ratio? What they are telling? Characteristics impedance Z0 terminator with the load ZR load impedance is ZR and ZR must be greater than Z0. They are telling. What is VSWR? Right? So VSWR is must be, we know VSWR should be greater than 1. S must be greater than 1. So out of this, which is having a value greater than 1? Because who is greater? ZR. ZR is greater than Z0. So which is greater than 1? ZR by Z0 less than 1. Right? We don't know about Z0 and ZR. So option A is the right answer. So ZR must be greater than Z0. So only this condition will give ZR by Z0 is greater than 1. So option A is the right answer. Fine. Right, so the VSWR of a microwave unit is the 1.5. What is return loss? Let me see the time and solve. Okay. So return loss we know minus 20 log of mod gamma. From VSWR, how can we find gamma? We know S is equal to 1 plus gamma divided by 1 minus gamma. Gamma is equal to S minus 1 divided by S plus 1. So first I find gamma. S is 1.5 minus 1, 1.5 plus 1. This is 0.5 by 2.5. That is 0.2. So gamma I found. What is minus 20 log of 0.2? That is equal to 12 dB. Right? So 1 by 5. So 1 by 5, 0.4. Only 2.5. Sorry. 2.5. It's 1 by 5, 0.2. So it is 0.2, 12 dB. 0.6. It is 0.2, 1 divided by 5, 0.2. These are the points. So it will be around minus 20 into log value find. So that is the answer. I don't have answer for this. Minus 20 log of 0.2 you find. Log 0.2, otherwise I find log 0.2. Log log 0.2. Log of 0.2. It is 0.69, right? 0.7 something, 0.7. So minus, where is it? Minus 0.7. So it is 20 into minus 0.1, around 14 dB. So the answer is 14 dB, right? Okay. Fine. This question is a beautiful question asked in GATE exam. Let us see. The voltage standing wave button in a 50 ohm resistance. So Z0 is equal to 50 ohm. And resistive load. They are given resistive load is shown in the figure. What is the value of load resistance? So they are asking about load resistance. Okay. So here you see this is VZ. It is x-axis varies with respect to Z. Y-axis varies with respect to VZ. So what is the maximum value? This is V max. This is minimum. So this value is maximum voltage is 4. V max is 4. V minimum is 1. We know S is equal to standing wave ratio V max by V min. So 4 by 1 is equal to 4. Right? So S is equal to 4, we got it. Then I have to find what is the value of load resistance. Right? So load resistance maximum Z max is equal to Z into Z0. This is the equation you must remember. I didn't explain this, but we must know. Z minimum is equal to Z0 by S. So easy to remember. Fine. So what is my Z0? They are given. Z0 is 50 ohm and S is 4, right? So what is the thing? S is Z max equal to Z naught is 4, Z naught 50, S is 4, it is 200. Right? So then Z in, Z minimum is 50 by 4, it is 12.5. Right? Okay. So we got Z max 200 ohm, Z minimum 12.5 ohm. But you see here which is occurring at the load. See, the maximum occurs at here only. Minimum is occurring at load. This is very, very important. Minimum occurs at load. Right? So the maximum is not occurring at load. Voltage minimum occurs at the load. So what is the minimum impedance? It is 12.5. So the answer is 12.5. If you put 200, this will be wrong answer. Right? Voltage maximum is 200, but at the load we have minimum. Right? We don't have maximum. Suppose if it comes here, then we have to find 200. Right? So that is a beautiful thing we must remember. Right? What is the reflection coefficient? We got S is equal to 4, gamma is equal to S minus 1 divided by S plus 1. So 4 minus 1 divided by 4 plus 1, 3 by 5.6. Right? So simple problem. What is the only twist you have to remember is where is D minimum? Right? And this formula you just remember. Right? Relationship between the impedance and S and Z naught, right? So load impedance maximum, load impedance minimum, that is given by S into Z naught and S, Z naught by S. And this is another question. Okay, this I will deal later because it is talking about adjacent voltage minimum and maximum. So when I deal all the things, then I come to this point. Okay. After dealing this, I can come to that point. This is a very, very important point. Open circuit and short circuit line. Right? So let me take some water. Fine. Okay. So how the impedance is distributed across open circuit and the short circuit line? This plays very huge role. Then only we can solve those problems. Right? So this you keep it very safely. This table is very important. Length of the line. Fine. Okay. Here equivalent circuit element. This question they ask in GATE exam, ISRO exam from this table only. I made it as table and I make you to understand very simple. Open circuit, short circuit. Right? Fine. If the length of the line is less than lambda by 4, right? So the open circuit line acts as a purely capacitor. Already we know what is the impedance of open circuit line, minus JZ naught cot beta L. So you see when length is less than C by 4, open circuit line acts as a capacitor, right? And the short circuit line acts as an inductor, right? So what is the impedance of short circuit line? We know already it is JZ naught tan beta L. Open circuit I told cot O to O, right? So this is very important. Length is less than lambda by 4, open circuit capacitor, short circuit inductor. Length is equal to lambda by 4, right? So when the length is equal to lambda by 4, open circuit line acts as a series resonance. Short circuit line acts as a tank circuit. Okay. This is the first thing. This table is very, very, very important. Proof is there. Hope you have studied in the class. Next. I write it in different color. Okay. When length is greater than lambda by 4, this acts as an inductor. This acts as a capacitor. So we know for open circuit line, as usual, same minus Z, J, Z naught, cot beta L impedance. This is J, Z naught, tan beta L. Here it acts as a, at L is equal to lambda by 2, it becomes tank circuit. It becomes resonance circuit. Right? Series resonance. Okay. Right? So this is very important. So how to remember, for length is less than lambda by 4, it is, we can call, right, OCI, for open circuit capacitor. Right? So open circuit OC capacitor. Right? For length is lambda. For length is greater than lambda by 4, short circuit inductor. You just remember this. Other thing you can do alternatively. For length is less than lambda by 4, open circuit capacitor, OC capacitor, right? Short circuit inductor. Clear? So in that way you can remember. But you must remember. You make your own way of understanding, but please remember this. Right? So open circuit capacitor less than lambda by 4. For greater than lambda by 4, open circuit is inductor. Simply you see OCI. OCI, open circuit capacitor and inductor. Less than lambda by 4, open circuit is capacitor. Greater than lambda by 4, it is inductor. Right? Like that you can do. You develop your own way of understanding. Right? Okay. Next. So how the impedance is distributed in the plot, you can see, and length is varying from 0 to lambda by 4. This is length. It is impedance, reactance XOC by R naught. So it will be like this. Hope you should have seen in your class up to lambda by 2. Open circuit, right? So you see in the denominator it is minus, it is plus. Minus means capacitive, plus means inductive, right? L. So you see less than lambda by 4, open circuit is capacitive. Fine. Greater less than lambda by 4, short circuit is inductive. Greater than lambda by 4, you see less than lambda by 4, it is capacitive. Greater than lambda by 4, it is inductive. You see less than lambda by 4, capacitive. Greater than lambda by 4, inductive. This is what open circuit line impedance distribution. Similarly for short circuit, right? Here you see for short circuit, it must be opposite. For 0 to lambda by 4, it is inductive, right? You have to do like this. Then it is lambda by 4. Here it is acting as a capacitor. Lambda by 4, lambda by 2, yeah. Fine. XSC divided by R. Numerator, positive means inductive, L. This is capacitive. So you see it is a short circuit. Less than lambda by 4, it is inductor. For short circuit, less than lambda by 4, it is inductor. Greater than lambda by 4, it is capacitor. Right? So this is the impedance distribution curve. Fine. So this we must remember. Okay. Next one is voltage and current distribution on the dissipationless line. Right? This is another important point. We know for dissipationless line, okay, let me write. If the line is open circuited load, terminated by open circuited load, current at load will be 0. Why? Since it is open circuit, load current is 0. First thing we must know about is V is equal to VL cos beta L. All the formula you remember. I is equal to JVL by R naught sin beta L. Right? So why this is, you see what is Z? V by I. V by I you do, Z is equal to V by I. VL cancel, right? I 1 by I is minus J. R naught will come to numerator, R naught. Cos by sin cot. That's what we know. For open circuit line, it is J Z naught cot beta L. Since it is a dissipationless line, so Z naught is equal to R naught. So Z is equal to minus J cot beta L. That's what voltage at the line for open circuit load. This is current is this one. Okay. Now you see very important. I told this is by using this we saw a lot of problems. Right? At load for open circuit line, current is 0. Right? I draw current diagram. So how? Right? You see, this is current. So you see, it is a load at load end, open circuit load. At load, I is 0. Right? This is it. What is V? For open circuit, we know I0, V is maximum. This is we know. Okay, let me draw for V. V will be like this. Fine. Okay. It will be like this. V is maximum. V max. Because for open circuit, voltage will be maximum, current is 0. Right? So you see, this is V max, this is V minimum. So this length is lambda by 4. You see, it is I minimum. Here, it is I max. I max. This is lambda by 2. So from this, what we understanding is distance between two adjacent maximum is lambda by 2. Why? Here you see, this is maximum. Where is another maximum for voltage? It is minimum. You come here, it is minimum. Again, here only maximum. So distance between this maximum, distance between any two maximum is lambda by 2. Very important. Distance between two adjacent minimum is lambda by maximum and minimum. Between maximum and minimum. You see, maximum is here, minimum is here. What is the distance? Lambda by 4. Minimum is here, maximum is here. Lambda by 2, lambda by 4, lambda by 4. So distance between two adjacent maxima or minimum is lambda by 2. Here you see minimum, the next minimum occurs at lambda by 2. It is 0. So distance between two adjacent maxima or minima is lambda by 2. Distance between maximum and minimum is lambda by 4. Very important. Right? So by using this only, we have to solve the previous problem. Okay, this is our open circuit load. Right? So you see, I will tell some other point whether time is permitting me. Okay. Here you see, here at x is equal to lambda by 4. This is the distance, let us assume distance x or L. At L is equal to lambda by 4. What is voltage? Voltage is 0. It is, this is at L is equal to 0. That means here, right? At L is equal to lambda by 4, voltage is minimum, I is maximum. So JVL by R. What is the maximum value? JVL by R. Because maximum value of sine is 1. So JVL by R. What is power? Power is equal to VI. That is Z. Right? Okay, fine. So this is the thing we have to remember. Next, for short circuit load, what is the at L0? V is JIL R naught sin beta L. I is IL cos beta L. What is that? V by I. So it is JR naught tan beta L. That's what we know already. Fine? Okay. See, at short circuit load, we draw the diagram. This is load, short circuit, 0, L. Okay. So what is the thing? At short circuit load, what will happen at the load at short circuit? V is 0. In short circuit, current is maximum. Right? So here current is maximum. It will go like this. So I max. Because at short circuit, current is maximum. What about this? It is maximum. The minimum occurs at lambda by 4. So it is lambda by 4. Next to maximum, lambda by 2. So distance between one maximum and another maximum, lambda by 2. This is 3 lambda by 4. Okay. Next, what about minimum? Voltage. Voltage at the load is minimum. So it is 0. Here it max. Here it gets minimum. Here it gets max. And again, at this point it is minimum. So here V minimum, that is equal to 0. V max, V max. Again, you see, distance between the maximum and the minimum is lambda by 4. Right? So distance between the two maximum is lambda by 2. This is maximum. This is maximum. Distance is lambda by 4. This is lambda by 4. So total distance is lambda by 2. Right? So distance between adjacent maximum is lambda by 2. Right? So this is the thing we have to remember. I hope you understand this. Right? Okay. When load is matched, third condition. First one is open circuit load. Second one is second one is short circuit load. The second case. First case. Third case is matched load. Matched load means ZL is equal to Z0. Right? So here you see the curve will be like this. This is V. Fine. So this is max. V and A. So this is what in the matched load. So here L is equal to lambda by 4. Fine. Everything is constant. You see, it's for max and minimum. Right? This is the thing we have to remember. And this one here V is VL equal to G beta L. Here I is equal to IL equal to G beta L. Fine. So this problem, for a short circuit in between lambda by 4 to lambda by 2. So you see short circuit in between lambda by 4 to lambda by 2, it is capacitor. So the question here you see the input impedance of a short circuit line of length where L varies from lambda by 4 to lambda by 2. It is capacitive elimination, right? So that is the thing they are asking. The input impedance of a circuit less than lambda by 4, greater than lambda by 4 capacitive, less than lambda by 4 it is inductor. So it is purely inductor. Fine. Okay, next we come to input matching. That is another important point. So, okay, sorry for the some disturbance, right? So net was connected. Let me start again, right? Let us start with impedance matching, right? So this is another important point we must know. What is impedance matching, right? So for achieving impedance matching, we have three system of devices we are going to study. One is quarter wave transformer, single step matching, and double step matching. Right? Impedance matching means what is the need? The load impedance must be equal to characteristics equation. This is what impedance matching. Why we need impedance matching? To transfer maximum power. We need impedance matching. So ZL is equal to Z0 will achieve impedance matching. Whenever we want to transfer maximum power, load impedance must be equal to characteristics impedance. In order to achieve that, we are having three different techniques. One is quarter wave transformer. Second one is single step matching. Third one is double step matching. Right? So first thing we are going to learn about is quarter wave transformer. Quarter wave transformer, it is an impedance matching device. It acts as an impedance inverter. Right? So it acts as an impedance inverter. That is the first thing you must know about this. And it couples transmission line to a resistive load, which is nothing but our antenna. Right? So this is the thing. It is the main role played by the. It is very, very important impedance matching device. Fine. Okay. So here you see. Okay. So the main formula you have to remember about this in quarter wave transformer, it is Z0 is equal to Z source into Z load. Here Z0 is characteristics impedance, source impedance, this is load impedance. Right? This is a very, very thing. By using this formula and this thing itself, you can solve any question in the GATE exam or TRB exam or CANCEL exam. Let us see. First question is, here you see the load impedance ZL 200 plus J, that is 200 ohm, is matched to be a lossless line Z0 50 ohm. So 50 ohm lossless line 50. By using a quarter wave transformer. What is the characteristic? So 50 ohm lossless line means they ask characteristic impedance. So it is input impedance. So what is characteristic impedance? ZO is equal to ZS into ZN. ZL. So what I told, ZL is, ZS is, or ZN. ZL or source impedance or input impedance. 50, ZL is 200, right? So that is equal to 10,000 square root, so 100. So the answer is 100, right? Simple question. Second question, a lossless transmission line having a 50 ohm characteristics. So Z naught is 50 ohm and length lambda by 4. Lambda by 4 means it is quarter wave. Why it is quarter wave? Wave is lambda 1 by 4 quarter wave. So don't forget lambda by 4 is nothing but lambda quarter wave. Lambda by 4 short circuited, not 1 ended, and connected to a ideal voltage source of 1 volt. Vs is equal to 1 volt. Right? So you see it is a transmission line. This is short circuited at 1 end. Right? Here the source is 1 volt. The length is lambda by 4. What is the current drawn? What is I value? Right? Current drawn from the source. We know I is equal to this voltage source Vs by Zn. Z naught we have. Right? Okay. So what is Zn? Zn, it is a quarter wave transformer. So Zn is equal to Zn into Zl, that is equal to Z naught square. Right? What is Zn? Zn is equal to Z naught squared by Zl. Yes or no? How I got this? Z naught is equal to root of Zn into Zl or Zs, source impedance into Zl. So Z naught squared is equal to Zn into Zl. Right? So Zn I want because I is equal to Vs by Zn. They ask current. See from this, what is ZL? ZL is load. Load is shorted. Load shorted means what is the impedance? 0. So Zn becomes infinity. When Zn infinity, what is current? Vs by infinity is 0. So the answer is option A. Right? Next question. The input impedance of a short circuited lossless transmission line of quarter wave law. Right? So what is input impedance? It is equal to Zn is equal to Z naught squared by Zl. Fine. It is short circuited. Sorry. It is short circuited. Short circuited means the line load impedance is 0. So Z naught square, it is infinity. Right? So short circuited, it is infinity. So impedance is infinite. So option is C. Next question, you see a very lossy lambda by 4. Lambda by 4 means it is quarter wave. 50 ohm transmission line. So Z naught 50 ohm. Open circuit. So load is open. Load is open. Okay. So quarter wave transformer, Z naught is 50 ohm. Load is open. At the load end, the input impedance. So load is open means ZL is infinity. Fine. So what is Zin? What is the impedance at the other end? Which is nothing but our input impedance. Zn is equal to ZO squared by ZL. ZO squared divided by infinity. So option A is the right answer. So how can you remember? You see the length is lambda by 4. 50 ohm. The characteristic impedance is 50 ohm. The load is open. So this is load open. What is the other end? Other end is nothing but input end, right? So Zn they asked. So Zn is equal to ZO squared by Zl. So this equation you always remember, right? Okay. First problem, ZL 200 ohm. Input impedance Zn 50 ohm. What is character? That's not only have done. It is 100 ohm. Already we did this in the gate exam question. So it is 100 ohm. Next. Here, a transmission line with the characteristics impedance 100 ohm. So Z naught 100 ohm. is used to match 50 ohm section of a to a 200 section. Okay. So a transmission line with a characteristic impedance of 100 ohm is used to match 50 ohm section to a 200 ohm section. So this let us assume this section is 50, this section is 200, right? So this is a impedance here, this is an impedance here, right? If the matching is done to be at 500 megahertz and 1.2 gigahertz. So F is equal to 500 megahertz and 1.2 gigahertz. At this frequency, we have to match. What is the length of the line? That is the question. So this is a critical question we have to do. Right? So let us assume this is load, this is source. So what is characteristics impedance? Characteristic impedance Z0 100. Okay. We want to find what is the length. Length always is represented in terms of lambda. Sorry. We know adjacent maxima lambda by 2. Distance between maxima and minima lambda by 4. So in transmission line, length is represented in terms of lambda. So I have to find the first lambda. They are given frequency, right? So you see lambda 1. Lambda is C by F. 3 into 10 power 8 divided by first frequency 500 megahertz. So 500 means 5 into 10 power 8. So it is 0.15 meter. What is second frequency? 1.2 gigahertz. Lambda 2. C by F2. 3 into 10 power 8 divided by 1.2 into 10 power 8. That is 0.25 meter. Right? So what is the thing? We have 2 lambda. See, this is matching 200 ohm to 550 ohm. It is frequency 1, it is frequency 2. If the matching, we have to do matching at 2 frequency. One frequency at 500 Hz and another frequency at 1.2 gigahertz. Right? So we got a lambda. If for matching 500, the length should be this one. For matching 1.2 gigahertz, the length of the line should be this one. Okay? But if I want to match both, what I need? I need a LCM. So LCM of 0.15 and it is 0.115. It is 0.15. Okay. So it is why it is lambda 1 is equal to, okay, sorry, lambda 1 we got as 0.6 meter, right? So for using matching, we have to use quarter wave. So lambda 1 by 4, it is 0.15 meter. Similarly, here lambda 2 is equal to 0.25 meter. Lambda 2 by 4, it is right. So 0.25, it is 0.25. Lambda 2 by 4, it is 0.0625. Right? So you see why I take lambda 1 by 4 and lambda 2 by 4. For matching, I need quarter wave transformer. So the length should be lambda 1 by 4. I found lambda 1 here, lambda 2 here. So for matching, I need quarter wave length. So lambda is wavelength. Quarter wave means lambda by 4. So it is 1.15 meter. It is 0.0625 meter. Right? So if I want a line which should match both these two, I have to find a LCM of these two. LCM of lambda 1 by 4 and lambda 2 by 4. Right? Sorry, GCD, common divisor. GCD of both. So if you take a GCD, what you get is it will be approximately equal to 1.35 meter. right? So how you see, if you multiply this by 9, it will be 1.35 meter. If you multiply this by 9 also, it will be 1.35 meter something. So what is the thing? It is the greatest common divisor. Fine. So by using this, I can, the length should be 1.35 because for first one will match at 0.15, then 0.3, 0.45, then at point 1.35. Like that it will match. Either the length should be 0.15 or 0.3. It is quarter quarter. For second one, it is 0.60625, right? 0.0625. It is 1 point, like that it will go, right? So it will be going, and at 1.35, both the lines match each other. Clear. So the greatest common divisor is 1.35. So 1.35 is the answer. So how I did 1.35 correctly? You take GCD, otherwise from the answer, you try to divide both the numbers, 0.15 by and 0.0625. Divide all the numbers by both. Which one is dividing? That is the answer. So option C is the answer. 7 to 1, you see, to maximize power, a lossless transmission line is to be matched to a resistive load of IR lambda by 4. Lambda by 4 is nothing but quarter wave transformer. What is the characteristic impedance? We know characteristic impedance of the quarter wave transformer is ZO, ZS into ZL. From the diagram, ZL is 100, ZS or Zin is 50. So 50 into 100, right? It is 5000. So the square root is 70.72 ohm. So the answer is 70.72 ohm. Sorry, excuse me. Next one, the last question. You see, two-wire transmission line of characteristics impedance Z0 is equal to, is connected to a load ZL. Z0 is connected to a load ZL. Impedance matching cannot be achieved. You see, cannot be. You know, quarter wave transformer is used to achieve impedance matching. Stub matching is used for achieving impedance matching. Short circuit parallel, that can be used for impedance matching. So half wavelength transformer cannot be used to achieve impedance matching. So this is the correct answer. This cannot achieve impedance matching. These three are impedance matching devices. Right? So simple problem. Right? So this also you can do like this. I told now you start from right. ZL, Zn, here Zn is ZO squared by ZL. Fine. So you see what is the question they are asking? Determine the impedance as seen by the source. This is the question they are asking. A transmission line terminates in two branches. Here you see it is going like this. The branches are terminated by 50 ohm load. So here you see this is the load 50, here load 50, here we don't know. The lines are lossless. That is very important. And have characteristic impedance shown in figure. See, for lambda by 4 line, Zn is equal to Z0 squared by ZL. Z0 squared is 100 squared. Here you see Z0 squared is 100 squared. ZL is 50, right? So 100 squared 50, 200 ohm. So here Zn is 200 ohm. Fine. Here Zn is Z0 squared, 100 squared, ZL 50, 200. So here also it is 200, right? So these two are splitting. So it is parallel, divided. So what is the load impedance here? 200 parallel 200 means it is 100 ohm. So for this load impedance is 100 ohm. So what is Zn here? Zn is Z0 squared 50 into 50 divided by, here load is 100. So ZL is 100. That is 25. So the answer is 25. So this type of question only you can expect in the GATE exam nowadays. Okay. Now we go to step matching. So stub matching also we know very clearly, right? So what are the things we must know about stub matching? So stub matching is used for impedance matching. Please remember, right? So what is stub? So stub is a transmission line only, right? So transmission line of small length, right? And it is connected at one end and the other end is open. Fine. So if you have a transmission line like this, right? So ZL. So stub will be connected at one end like this, right? So other end is open or short, right? Okay. Or other end is either open or short circuit. Okay. So that is the first thing we must know. It is used for impedance matching, and it is a transmission line of length, small length, and it is connected at one end. This is the end connected, and the other end is open or short. Fine. And input impedance of a stub is purely reactive. Right? That means either capacitive or inductive. First thing you have to know, depending on the length of the line. Depending on length of the line. So that is the thing we have to know. Right? Okay. Stub can be considered as frequency dependent inductor or capacitor. So these are all the points you must know whenever you want to work with the stub matching technology. Okay. Next, we know we have two stubs. The stub may be open or short. So short circuit stub first. For short circuit stub, ZSC is equal to J Z0 tan beta for lossless line. We know already. For short circuit, Z0 impedance is Z0 J Z0 tan beta L. Depending on whether beta L is positive or negative, stub will be capacitive or stub will be inductive or capacitive. Why? You see, when beta L is positive, tan beta L becomes positive, right? So beta L is positive means tan beta L positive. This implies tan beta L positive means Z0 is always positive, so it is a lossless line. So ZSC is positive. So impedance is positive means it is inductive in nature. If beta L negative, tan beta L becomes negative. So ZSC becomes negative. So what happens? It is capacitive. Right? Similarly, for open circuit stub, what will happen? ZOC is equal to minus JZ0 cot beta L. So what happens? Depending on beta, right? Reactance may be capacitive or inductive, right? So if beta L is positive here, what happens? Beta L positive means ZOC becomes negative. So no, beta L positive means this is cot beta L positive, so ZOC become negative. So what will happen? It is a capacitive reactance because for capacitive, a reactance is negative. So that is the thing. So it is alternate, opposite to the whatever happens here. So depending on beta L is positive. If beta L positive, what will happen? Tan beta L become positive. So the short circuit impedance will become positive. Positive means it is inductive. Similarly, if beta L become positive here, cot beta L become positive. So ZOC becomes negative. So it is capacitive. Similarly, beta L is negative, cot beta L negative. So this becomes ZOC becomes positive. So ZOC is inductive in nature. Right? So that is the thing we must know about open circuit and the short circuit. And we prefer short circuit stub is preferred. Why we prefer short circuit stub compared to open circuit stub? Because it radiates some power out. So power loss may occur. So short circuit is preferred compared to open circuit. That is very, very, very important. This question they may ask, right? Which stub is preferred, whether open circuit stub or short circuit stub, right? Okay. Next thing we have to remember is two stub. First one, we have two stub for impedance matching, single stub and double stub. Fine. What's the time? Okay, I finished it in 5 minutes. So single stub matching and double stub matching. Okay, so in single stub, what we do? In double stub, what we do? Fine. So single stub is used for fixed frequency and impedance, right? So here location and the length of the stub is fixed. Fine. Here location is fixed, length may be varied. So the length may be varied in double stub matching, right? So it is suitable for fixed Z. So if Z varies, right, what happens? We have to length and location of stub should be changed. So it is very difficult. So this is the main disadvantage. Z is nothing but load impedance. So if load impedance varies, because our load is going to vary regularly. So if load varies, the length L and the location of the stub should be changed regularly. That is the biggest drawback of single stub matching. Right? So that is the first thing we must remember. Okay, so double stub matching avoid that problem. How it avoids that problem, let us see. Right? So what we are doing in stub matching here, stubs are positioned, stub is positioned right at a distance. This is very, very important. Please listen carefully. I write properly at a distance from load. You see, you mark the word distance at a distance from the load, right? So here D is a distance which is chosen so that at that point, right, resistive part of ZL, load impedance is equal to resistive part of characteristic impedance. That means we know impedance is given by R plus JX. So D must be chosen in that circumstance let us assume Z0 is equal to R0 plus JX0. ZL is equal to RL plus JXL. We have to choose D where R0 must be equal to RL. That is the location of stub, right? So then length is chosen, right? So that it exactly cancels the reactive part of the Z0. So you know how to choose a length. See, first we must remember this is a line, fine. This is Zin, ZL, this is a transmission line. This is a characteristic Z0. Here I am choosing. Let us assume this is a location. So how to choose this distance D? This is the position of the stub. How can I distance D? Here, the real part of Z0 and real part of ZL. That is, resistive part must match. So at this location, this is the stub I fix. At this point, let us assume AB. At this point, AB, R0 must be equal to RL. That is, the real part or resistive part of the impedance must be equal. What is the length? This is the length of the stub. So the length of the stub is chosen such that the reactive part, it exactly cancels the reactive part. So you see at this point the reactive part, if it is capacitive, then Z0 must be, if Z0 here is capacitive, let us assume here the characteristic impedance as a capacitive reactance means stub should have inductive reactance. Why? Because reactive component should be cancelling. So the reactive component of the stub should cancel the reactive component of line. So let me assume line has capacitive reactance. If line has capacitive reactance, the stub should have inductive reactance. Then only these two reactants will be cancelling. Suppose if the line has okay, if the line has what you call, if the line has inductive, okay, if the line has inductive reactance, then stub should have capacitive reactance. Fine. So then only these two will be cancelled. Like that, we have to choose the length. We know the length of the Z can be equal to J Z naught tan beta L. Just now only we have seen when we have a capacitive and inductive reactance, right? Last I told. So depending on the beta L, the reactance may be capacitive or reactive. So choose the length such that if the line has a capacitive reactance, the length of the stub should be inductive. If the line has inductive, the length of the stub should be capacitive, right? So in this way, we have to choose the length of the line, the location. This is talking about location of stub. Location is chosen based on the resistance. Length is chosen based on reactance, right? Length of stub. Right, so it is depending on R, it is depending on Jx, right? So if the line has plus Jx, that means inductance, the stub should have minus Jx, that is reactance. Then only they will cancel each other. So in this way, stub matching is achieved in the you should achieve what you call impedance matching. So reactance cancel. So R is equal to R0. I told already R0 is equal to R0, RL, that is a impedance matching. That's what we achieve impedance matching. Reactance will be cancelled. Load impedance is equal to characteristic impedance. So maximum power will be transferred. So in this way, stub matching achieves maximum power transfer. That's all about this session, right? I hope you understand everything, right? Surely you should have some doubts. If you have doubts, please ask me. I am happy to answer all your doubts, right? So you can contact me at any time. So my WhatsApp number you see 9944536375. So my YouTube lectures you can watch it on MEAJE lectures. Right here I have solved a lot of TRB, uh, right? Answered questions and moreover gate. Right? So if you want to know in detail about EMF, refer my EC8451 playlist. Right? It is purely covering gate syllabus. And even though it is Anna University syllabus, so I solved a lot of, I taught in a gate-oriented way. So surely this playlist will be useful, right? So refer my playlist EC8451, right? So it will be opening a detailed analysis of all the EMF concept, right? So thank you for patient hearing. Thank you. Any doubt you can ask.